So here we go. We're going to study the fundamental counting principle. And I'm just going to talk in general about it first, and then we'll get into notes. The fundamental counting principle was developed thousands of years ago by mathematicians. Blaise Pascal was probably one of the first mathematicians to really sort of formalize this or finalize this concept. Those of you who go into computer languages, Pascal is a computer language. He not only did work in math, he also, you know, he's one of those Renaissance guys. He's got some writings, he's got some art, he's one of those cool guys who did a whole bunch of different things. His contributions to the world of probability and then the branch of that off to statistics is really huge. He did a lot of great things for that particular area of mathematics. Anyway, the counting principle is this idea that if, like I want to take a month and eat as many different kinds of ice cream cones as I could from one particular store. So I would have to know how many different flavors of ice cream they had, and then I could calculate small, medium, large, supersize, whatever their options are for different sizes, toppings, you know, sprinkles, peanuts, whatever the options are. I could calculate how many different combinations of ice cream I could have, and probably I wouldn't be able to eat them all in just 1 month. If I had them for breakfast, lunch, dinner, and snacks.
5 different times a day.
Right, exactly. So that's one example. If you, and I thought about this morning, if you were, say, a car dealership owner, and you wanted to say, you know, we've got a ton of cars, lots of options for what you can purchase from our lot, you might, instead of counting up each car, you might say, well, I have 480 different possible combinations by the time you have color, 2 doors, 4 doors, manual or automatic transmission, all, you know, sunroof, not sunroof, moonroof, not moonroof, whatever. So you could advertise, you have all these different possible car combinations that somebody could come to your lot and purchase, which is really cool if you're in the market for a car, and also you want to sort of advertise how great your dealership is, how many options you have. So knowing that number could be helpful as far as marketing goes. To get that number, you need the fundamental counting principle. And there's sort of 3 components of the fundamental counting principle. The first is what we call a tree diagram. And I'll show you what these mean. You've probably had some experience with them before. I don't call this the ordered pair. I call this a, what do I call this? Sample space. That's not what I call it. Hold on, it'll come to me, and then I'll fix it. And then the third, and that's what we're going to spend our time on in the back, is the straight up fundamental counting principle. So let's jump in and, oh, that's what I call this a list. Yeah, it's that simple. I couldn't. It was that crazy of a day so far. So all of these give us the outcomes or the results of something happening, the results of an experiment. And they're all different ways to talk about something called a sample space. So at the top I've highlighted and circled or underlined those. All right, let's jump into number 1. We have the Sunday Palace that has how many flavors of ice cream? How many? 5. What they like to do is list them all, but before that you have to look and find the number 5. You certainly can count them up, and you're very capable of doing that. They don't ever give us crazy huge numbers to work with. A sundae can be made with either fudge or caramel topping. So how many topping choices do we have? 2. And you can't have both, so it's just fudge or caramel. A sundae will be made that consists of 1 scoop of ice cream and 1 topping. I know, who makes a sundae that small? Yeah. I don't understand it, but just go with it for now.
I do.
So our experiment is making a sundae
feel like we're in science class.
Yeah? And be sure you spell that type of Sunday correctly. It's not the day of the week. And our outcome, the result of the experiment, bless you, is 1 scoop of ice cream and 1 topping. So, I'm going to do the tree diagram first and then we'll do the list. The great news is, on the Regents, on your quiz this week, you're only going to have to do it one way or the other. So pick a way that you are okay with and be good at it. You don't have to do them both, okay? On your homework tonight, we ask you to do it both ways just for another time of practice, but when it comes to being assessed on it, you have to be able to do one or the other.
If you multiply 5 by 2, would that give you your answer?
That's the fundamental counting principle. That doesn't give us our tree diagram or our list, but it tells us how many we should have. Yes, you're absolutely right. Okay, so to do a tree diagram, you start with either the 5 or the 2 from your problem. And I don't care, I always start with the bigger number because I just do. It's probably how my teacher taught me back in the old days. So we have vanilla, chocolate, strawberry, peach, or raspberry. I label them right on the line. I had a student this morning that said, can I put them at the end of the line? And you certainly can. As long as they're there somewhere. Don't do them twice. The red is another option. Don't do them twice. The red is another option. Don't do them twice. The red is another option.
Got it.
Bryce, you with me? Okay. After you've chosen your 1 flavor for your 1 scoop on this ridiculous Sunday, but yes, then you have 2 options for the fudge or the caramel. Fudge or caramel. Fudge or caramel. Fudge or caramel. And again, you could have the F's and the C's at the end of those branches as well if you'd like. I don't care. I always write them on the line, but if you want to put them at the end, that's completely fine, completely legal. Now, a couple minutes ago, Nick said, can't we just do the 5 times 2? And that tells you how many Sundays you're going to get. Yes, you can. Yes, you can. So we're going to get 10 Sundays.
We've got a lot of numbers.
Then you're not going to make a tree diagram or list the sample space, because that's too crazy nuts.
I mean, like, more, like, not a lot of numbers, but like, more options, like.
Then you just keep branching out. They don't have us go past 3 branches. Yep. And we're going to do one of those in just a minute. So, do you see anywhere on here, on our tree diagram, where there are 10 Sundays listed? Somebody tell me where. What part are you looking at? Macy, what do you see?
Count all the F's.
All the F's and C's at the end. So my green should be a total of 10. Perfect. That's exactly where we're going to look, is at the very end of our tree diagram to tell us how many Sundays or whatever we have. Great, thanks. All right, if we're going to do the list, then we're going to start with our vanilla, and we can either have fudge or caramel with that. And then we'll move to our chocolate, and we can have fudge or caramel with that. And then strawberry, and again, fudge or caramel, peach and raspberry, fudge or caramel. And again, there should be 10 there as well. So this sample space, this list, is just a list version of the tree diagram. Take a quick look and see. If I'm talking about how my tree diagram and list are together, so I could do the vanilla with the fudge, I could do the chocolate with the caramel. Okay, so I can follow my branch on the tree diagram and get the list, or the list can go back to the tree diagram. Again, be sure you're good at one of those, either tree diagram or list. I don't care which one. So you've got to be good at it
Don't get what you just did with the highlighter part.
with the highlighted part. All I said was, my first entry in my list comes from the very top of my tree diagram.
Alright.
And then down here a little further, the CC comes again from my tree diagram.
Okay.
Okay, number 2. A coin is tossed 3 times in a row. Brandon, you asked about what happens if we go more than 2 options. Here's a 3 option one. Represent all the outcomes in the sample space of this experiment by creating a tree diagram and a list. Okay, again, I would call this a list. All right, so tree diagram. We have 3 coins, or a coin we're going to toss 3 times. So the first time we toss the coin, what's our option? Heads or tails? Same coin, we're going to toss it a second time. What's our option? Same coin, we're tossing it a third time. Yeah? All right, somebody help me. I have the option of heads or tails, and I'm tossing it 3 times. How in the world did I get 8? Because I'm thinking that my heads or tails times my 3 coins is only 6. So what happened there? Well, this is a fail. In the first option, how many, go ahead. Where'd the 4 come from? Oh, because there were 4 greens? And that's going to get us our 8 at the end, is what you're saying? Kind of. Kind of. The first time I toss the coin, how many options do I have?
2.
And the second time I toss the coin, how many options do I have? And the third time I toss the coin, how many options do I have?
2.
And 2 times 2 times 2 is 8.
So instead of 2 times 3, it'd be 2 to the third.
Mm-hmm, right. Good. Let me slide back up quickly to the sundaes and talk about that. In my first option, to make a sundae, I can choose what? What's the 5 represent?
The flavor?
Right, I can choose 5 different flavors of ice cream. That's my first option. Come back down to the coin. In my first coin, what are my options?
Heads, tails.
Heads or tails, that's my first 2. Go back up to the sundae. What does the 2 represent?
Fudge caramel.
My options for my topping. Come back down to the coins. What does this middle 2 represent?
The heads or tails.
Yes. Okay, so it's the same scenario, but instead of having different numbers for each option, the 5 and the 2 for the sundaes, I have the same option for my coins, heads or tails. All right, so our list. In my first toss, I could get a head. And in my second toss, I could get a head. And in my third toss, I could get a head. And I'm going to use those same colors so that it kind of makes a little bit of sense, maybe. Going back and starting over again. In my first option, I could get a head. In my second option, I could get a head. But in my third option, I could get a tail. When I do sample spaces, I always do a tree diagram. And then I do the list after that. But I always do a tree diagram to start, just because I am that weird. So I've exhausted all of the red head tail options. So now I've got to move to my greens. And I have an option of a head or a tail. Hold on. And then, yep, I'm good. So then I can go ahead or a tail with my second one.
For this one, the tree diagram.
I agree. Whoops, this needs to be an H, I'm sorry. Let me not do them ahead. I'm getting myself confused. I'm not wrong, I'm just not gonna go ahead. All right, so, head, tail, head. All right, so that's it for getting ahead on the first toss. There's no other options for getting ahead on my first toss. I've got red heads and tails and I have green heads and tails covered, okay? So now, if I got a tail on my first toss, I could get a head or a tail on my second toss, and then I could get a head or a tail on my third toss. There are a lot of different ways you can make that list. A lot of different ways you can make that list. And if my way of explaining it or just listing them down right now did not work for you, but you have a good method, have a great time. I have no problem with you doing it your own way. My only concern is that you end up with the right answer. Okay? How you get, are you two done?
Yes.
Great. How you get to that right answer, I sort of don't care. Okay? As long as you get there, I'm good with that. Let's jump to the back, please. In the back, we're going to look at just number crunching. We're not going to make any tree diagrams or list any sample spaces. So we're going to find just the total number of outcomes. Again, we're not going to list them off individually. We're not trying to follow what our options are. And to do that, we're just going to multiply. So, exercise number 3. A store has 10 different types of shirts and 12 different types of ties. So this is one where I thought of, oh, that'd be great advertising. You could make a nice commercial about how many different shirt-tie combos you could come up with for a men's clothing store. So it'd be the 10 shirts times the 12 ties, and that's it. There's 120 different shirt-tie combos. That's all the work you have to do. That's as hard as the math's going to get. That's it. That's not to say that the 120 shirt-tie combos are going to look good necessarily. Okay? Plaid shirt, striped tie might not be the best way to show up for work, but it is a combination of a shirt and a tie. Exercise number 4. Michael, Jacob, and Freddie are running in a race in which there can be no ties. So how many different orders can they finish in? So in other words, we need to have somebody come in first place, somebody to come in second place, and someone to come in third place. How many different ways can those 3 runners end up in first, second, and third place? How many runners could come in first place? How many are there to pick from?
3.
There's 3 runners, so any one of them could come in first place. And then second place, how many people are left to come in second place? Only 2. And then how many people are left for third place? Just 1. So you were right, Brandon. There are 6 different ways they could finish. 6 different orders.
I just kind of listed more.
Okay? Yep. That wouldn't be a bad list to make. So in number 4, we could ask you to do a sample space or a tree diagram. Because 6 is pretty manageable. We will not ever ask you to do sample space or tree diagram for 120. Ever. Okay? It'd probably take you way too long. And lots of pieces of paper.
3 hours. Just listening.
Right. But what we do like to ask you to do is consider license plates and the different combinations of license plates, letters and numbers that you have. I want some numbers written down here, not just a 6. So, in California, they're trying to do a new license plate system. They want 7 characters, and they're gonna use the 26 letters in our alphabet and 10 digits. Yep, so 0 through 9 gives us 10 possible digits. Notice they're not calling them numbers, they're calling them digits. All right, so the first 3 characters must be letters, and the last 4 must be digits. And we are allowed to repeat. So, in those first 3 spots, we have to put letters, which we can repeat them. So how many letters do we have to pick from for the first? Okay, and how many letters do we have to pick from for the second?
26.
And the third? Okay, now we're gonna move to the digits. How many can we pick from for the first spot? 10. And how about the second?
10.
And third? And fourth. And if you don't mind, I'm just gonna give you this number. If you wanna try it on your calculator, have a great time. But it is 175, comma, 760, comma, 000. 175,760,000.
I don't think there's that many people
Well, it's the state of California.
I don't think there's still that many people.
This is your first season.
There's a lot of people. And some, a lot of homes have 2 cars,
Yeah.
right?
Some have more than one vehicle.
Right. And then sometimes in California, there's a lot of Hollywood movie stars who have, 6 Corvettes and 12 Porsches
That's not
and
even fair.
whatever.
All those charging cribs.
All right, back to our own reality. Letter B, we have 3 letters to begin with, and then 4 digits to end with, but this time, no repeating. So we still have our 3 at the front and our 4 in the back. We probably should move that over because this number is kind of big as well. So, starting off, how many letters do I have to pick from?
26,
And then how about after that?
25,
Because I'm not repeating,
24,
things are decreasing. Very nice. Bryce, thanks. And then how about for numbers?
9,
10,
9,
9, 8,
7.
7. Now, don't touch your calculators. Anybody want to guess? Is it going to be less or is it going to be about the same? Okay.
Of course.
Is it going to be like half as much?
It's gonna be
A lot less.
A lot less?
Yeah, it's gonna be like 1,000 less.
For
Yeah, a lot more than that.
You ready?
Thousand
Sorry,
million
this
less.
is just, it doesn't matter what numbers we use, right? Oh, man.
For where?
For the second.
I was gonna say it's gonna be like.
With this one?
Oh, that was nice.
Does-
That's a whole lot.
What do you mean it doesn't matter what numbers we use? What do you
Like, say it's a 10, 9, 8, 7, we could use different.
No, it has to because you have all 10 to pick from to begin with.
Yeah.
You use that one, so you have to start with 10.
Then
Then it's one less. Am I not understanding your question? Okay. So about 1 million less by not allowing repeating.
Well, that's a lot less options.
It is. Something for the state to consider.
said.
And then letter C. Again, we're doing the 3 letters and the 4 numbers. But what do we know?
Letters can repeat.
Okay. So letters can repeat, but numbers are not repeating. So somebody tell me, what are my letter spots what are those numbers gonna be? All 26s, good, because they can repeat. And then my numbers are gonna go,
10, 9, 7.
All right.
100 one.
Compared to this 78 million number,
It's gotta be more.
gonna be more than this, but less than the 175?
It's 126.
125.
Whoa,
Oh, I forgot
that's a
the second.
huge number.
Missing, I don't,
It's about 10 million more by allowing just repeating of the letters.
That makes more money for
Right, because everybody's gotta buy new license plates, so that's a great moneymaker for the state, right?
So they would actually make people buy brand new licenses,
Yeah, they're doing it in New York right now.
really?
Yeah,
They're just not,
you have to buy the yellow, blue ones.
What if you don't?
Oh, look, aren't
Oh,
they
they give you a
older ones?
phase-in period. Yeah, the retro.
what if you already have?
Okay, so fundamental counting principle, tree diagram or sample space. Be amazing at one of them. I don't care which one it is, okay?
Can you do both?
Yep, yep. And then, this fundamental counting principle, we're just gonna ask you for how many. We would never, ever ask you to list out all the combinations of these license plates.
But is he gonna ask you to show your work on the regions?
Your work for like these license plates is this little, this
Okay.
blue-red. Yep, that's all you have to show. Correct. Yep. And the tree diagram or list of sample space, just like we did on the front, that's all we have to see on the regions. All right, thank you.